Hello, everyone. Welcome you back to study MA4822, which is a course about the measurement and the sensing system. Today, we move on to study the lecture on measurement of acceleration. As usual, before we enter the study of today's lecture, let me give you a quick overview or review about the answer to these four common questions that you may have in mind. Question number one, why to study this course? Question number two, how to study this course? Question number three, what are you going to study from this course? And the question number four, how to learn the knowledge from this course. All right. So let me start with the answer to this first question, which is about why to study this course. All right. So by now you should know that our mission on Earth include the understanding of the world and the improvement or change of the world. Right. Then how to understand the world? We need to have sensory data. Then how to obtain sensory data? We need to have measurement and the sensing system. All right. Then how to improve the world? The answer is to develop a smart system, smart products, smart machine. Then how to develop these system, these product, these machine? The answer is to incorporate closed loop feedback control system, right? Then what is a closed loop feedback control system? The answer is it is a system which consists of three basic modules or three basic building blocks. One of them is a measurement and the sensing system. Therefore, you know that the study of this course is extremely important, not only for human being, but also for smart system, smart machine, and smart product. For example, in this slide, you will see the requirement for us to develop a smart parking system, smart street lighting system, smart building system, smart home system, smart environmental system, smart health system, and also Internet of Things, which could be deployed in the city area or in nationwide, right? So one of the key device inside the Internet of Things should be sensor, right? So you understand, okay, the motivation behind the study of this course. All right. Then the second question that you may have in mind is about how to study this course. All right. So my advice to you is to put yourself into the mindset of a designer. Then with the keyword design or designer in mind, automatically you will ask yourself these four questions. Who are the user? What are the need of the user? What are the functionality of the product or system that you are going to develop in order to meet the need of this user, right? Then what should be the solution behind the design of your product or your system, right? So for answer to question number one, should be human being and smart product, smart system, and smart machine. Answer to question number two should be the need to have sensory data, right? The answer to question number three depends on the specific nature of the user. For example, a car may require a certain type of a sensor, and the robot may require another type of a sensor, all right? So the answer depends on the specific nature of the user, all right? Then answer to question number four should be to study this course. At the end of the study of this course, you will know the solution behind the design of a sensor or measurement and the sensing system, or Internet of a Sensor or Internet of a Things. All right. Then the third question that you may have in mind is about what are you going to study from this course, all right? So basically this course will cover the study of physical principle behind the design of popular sensor in electronic domain, in mechanic domain, in environmental system, and in intelligence system. This course will also cover the basic detail about the physical world, the basic detail about the conceptual world. This course will also teach you the basic knowledge for you to deal with randomness or to cope with randomness, and for you to understand the phenomenon of fuzziness in the conceptual world. All right, so this slide basically show you the scope of topics that you are going to study from this course, all right? Then the fourth question that you may have in mind is about how to apply learned knowledge from this course. The answer is to follow the guideline shown by this slide, okay? Because we want you to apply learned knowledge in order to design sensor or measurement and the sensing system, or Internet of a sensor, or Internet of a sensor, in which sensor are one of the two major category of devices, right? Then how to develop sensor related product or sensor related system. Basically, you just follow the guideline in this slide, okay? So for example, the design of a sensor related product or related system involve two steps. Step number one is to transform the value of a physical quantity on the measurement into readable value, okay? For step number one, you may face two situations, all right? The first one corresponds to the case in which you just need to use a single front-end sensing element, okay, in order to obtain a readable value, right? But in most cases, you may face the second situation in which you have to make use of a front-end sensing element plus back-end sensing element in order to obtain a readable value, right? Then the second step involved in the design of a sensor-related product or sensor-related system is calibration. So calibration is a very simple process, but it is an extremely important process, because with the calibration, the output from the sensor should be exactly equal to the input of the value of the physical quantity on the measurement, all right? In addition, the unit of a measurement assigned to the output should be exactly equal to the unit of a measurement of a physical quantity on the measurement at the input, all right? So calibration will help you to basically rectify the error and rectify the unit of a measurement. This is because the output from a sensing element may have a value or may have a different unit of a measurement, which could be ignored totally, all right? Because we have a second stage, okay, or second step, which consists of a calibration. After calibration, then we can assign, okay, the same unit of a measurement to the output, which is equal to the unit of a measurement of a physical quantity at the input. All right, so this slide basically gives you the detail, okay, about how to apply learned knowledge from this course. All right, so now we are ready to enter the study of today's lecture, which is about the measurement of acceleration. So actually, acceleration is a very, very important physical quantity in mechanic domain, because acceleration will allow us to change velocity, and the velocity will allow us to change position. So therefore, the control of acceleration is extremely important. And like in the case of velocity, acceleration is also a vector. Therefore, we can talk about the acceleration along the x-axis, acceleration along the y-axis, acceleration along the z-axis. All right. If we are able to measure acceleration in one direction, then we can put the three measurements together. Okay. Then in order to achieve the measurement of acceleration in three directions. Okay. So it's just a simple mathematical addition. All right. So the key focus is to know how to measure acceleration in one direction. All right. And we know that in physics, there are three types of motion: linear motion, angular motion, circular motion. All right. So if we know how to measure linear acceleration, then you may ask this question: how to measure angular acceleration? All right. The good news is that we will leverage on the use of force in order to determine acceleration. And the good news is that the angular motion will induce centrifugal force, and the linear motion will induce inertial force. All right. And both forces could be considered as a force in a single direction, because the centrifugal force is in the direction, is in the radial direction. All right. So we can treat the radial direction as a linear motion. All right. So this is a background knowledge for you to know. Okay. If you know how to design acceleration sensor for linear acceleration, more or less you should be able to design acceleration sensor for angular acceleration. All right. So the mathematical principle is quite straightforward, and later on I will show you a little bit more detail. All right. So this is why we do not have a separate lecture on measurement of angular velocity, or to have a separate lecture to talk about the design of a gyroscope. All right. So actually the working principle is more or less the same. All right. So in practice, you can come out the hybrid sensor with 6 sensor elements inside. One to measure linear acceleration in x direction, another to measure linear acceleration in y direction, another one to measure linear acceleration in z direction. And similarly, you have 3 other sensor elements to measure angular motion about the x-axis, angular motion about the y-axis, angular motion about the z-axis. Then you can put them together. Then you have a 6 degree of we can name it as a 6 degree of acceleration sensor, or 6-axis acceleration sensor, right? So it's quite straightforward. So physically, you just add them together, all right? So our focus is on the study of how to achieve the measurement, direct measurement or indirect measurement of one component along one direction, right? So before we look at the solution for us to do indirect measurement and the direct measurement, it is very important for us to do a little bit revision about the physics related to acceleration. All right, so I guess every one of you have studied physics in year 1, then you know what is acceleration. Okay, so it's always good for me to give you a quick review or quick overview about the acceleration. All right. So acceleration is a very important physical quantity under control, not only in robotics, but also in industry, etc. And here is an example. All right. For this type of motion, you see acceleration is very important. Without acceleration, the robot will fall. All right. So you see, it is acceleration in the vertical direction, right? All right. Then this is another application in inside the smart product called the vehicle, smart vehicle. So every one of you may know that there is an airbag sensor. Then how to trigger the release of airbag, okay? So we must have the acceleration sensor to detect the collision, right?
This is an airbag sensor. It's responsible for detecting sudden deceleration in a car crash. On these Toyotas, the airbag sensor is usually bolted to the radiator cradle. Here's how to access the airbag sensor under the headlight. We remove the side marker, and remove the headlight bolts. I'm going to remove the bolts for the grille, and I'm going to pop the grille off. Pull out the grille, and remove one more headlight bolt, and then remove the headlight from the car. This here is where the frame connects to the bumper rebar. This is the airbag sensor. To remove it, there's one 12mm bolt and one electrical connector that needs to be removed. Here's an overview of how the airbag system works. The airbag sensor senses a deceleration during a collision and will send a signal to the SRS computer. The computer will also use the vehicle speed, yaw rate, and seatbelt occupant information to determine if an airbag needs to be deployed. It'll then send a signal out to that appropriate airbag, whether on the driver's side, passenger side, or one of the side airbags, as well as a signal out to the ECU to cut the engine off during a collision. This here is a ball and tube type of airbag sensor. It's basically consists of a ball and a tube, as well as a magnet, with a pair of contact switches here and a diagnostic resistor. The system uses this diagnostic resistor every time on startup to make sure the sensor is functioning correctly. Normally, the ball would be attracted to the magnet, but under rapid deceleration, the ball will dislodge itself from the magnet and cause these two switches to contact each other, sending a short circuit out to the SRS computer. This is the kind of sensor that's in my car right now. Basically consists of a small cam, as well as two contact switches and a diagnostic resistor. Driving along normally, this cam is free to bounce back and forth. However, under rapid deceleration, the momentum of this cam is enough to overcome the spring force of this switch, sending a short circuit out to the SRS computer. This is what the sensor looks like when it's removed from the vehicle. As you can see, rust is probably one of the common reasons why these things fail, because they're located on the front of the vehicle where all the salt and moisture build up. Let's open this guy up to see what's inside. Pry up here. We pull off the connector. Here we've got these metal tabs here that hold in the sensor. Just going to pry those over. Remove the sensor. Here's the sensor removed from the housing. It's quite a sealed unit. So I'm just going to go around here with the blade and cut it open. Just looks like all this stuff here is just epoxy or glue. I'm just going to cut it out. Okay, so I've got all the glue off. I'm just going to continue prying at the plastic here with my pliers. All right, I've got all the plastic removed from around the sensor. I'm just going to pry up on it right here, revealing the circuit board inside. Then I'm going to pry up on the circuit board slowly and remove it from the housing. Here on the circuit board, there's a little resistor on there that's used for the system check every time the car starts up to make sure the sensor is valid. These are the two terminals that come together when the vehicle experiences rapid deceleration, sending a short circuit through the two wires back to the airbag computer. Now inside this sensor, there's a little cantilever thing here that moves back and forth on a shaft. Now when the sensor experiences rapid deceleration, such as in a collision, that little shaft will move forward and make contact with the two leads on the circuit board here. All right, I'm going to attempt to remove this little cam by prying it out. And that's how we've got the shaft, as well as the little cam wheel that activates the sensor. So this is how the little cam wheel will engage the two terminals, completing the circuit. So that pretty much sums up what's inside the mechanism that they put.
All right, so you will see this is a very important safety application in automobile. And actually, you can also go to Singapore's car repair workshop and ask the owner to give you a used one. Then you can also dismantle it to understand what is the inner structure, okay, etc. So this is a typical application, and it is also a popular application in the world, all right, with the use of acceleration sensor, right? So in the physical world, this just remind you about these three types of basic motion: linear motion, angular motion, circular motion, all right? Linear motion means movement along a straight line, there's only translation, all right? Angular motion means rotating about the axis. All right. For example, in this case, this arm R could rotate about the axis which pass through point O, which is perpendicular to the screen. All right. And an object may follow a circular path. Let's say this point A follow the circular path, then the point A undergoes circular motion. All right. And in practice, normal motion is a combination of these three types of motion. All right. And from this drawing, you will understand when there is a circular velocity, automatically there is a centrifugal acceleration in this direction, or radial acceleration pointing toward the center of a rotation. So this is a radial acceleration or centripetal acceleration. This is a centrifugal acceleration. Okay, so it's pointing outward. So this is an inward, and we can also talk about the tangential acceleration or circular acceleration. All right. So I hope you understand the meaning of this type of acceleration. All right. So then what is the acceleration? By definition, acceleration basically means the time rate change of a velocity. When there's a change of velocity, it means there's acceleration. All right. For linear motion, we have this equation. For angular motion, we have this equation. So these are the basics in physics. All right. Then why there's an acceleration? What is the cause behind acceleration? Then we just apply Newton's second law. Okay, the cause behind acceleration should be the net force. All right, the net force will produce acceleration on the body in which the net force is acting. Okay, so the answer to this question is quite straightforward. Okay, so as long as there is a net force acting on the rigid body, then there is acceleration. Okay, for linear motion, the equation is equal to F divided by mass. Okay, for angular motion, then the equation is equal to torque divided by moment of inertia about the rotation axis. For a same mass, if we change the axis of rotation, the moment of inertia I will change also, right? So I, for a rigid body with a constant mass, is not constant, all right? Because when you change the axis of rotation, I will change. But here, normally the mass is a constant, all right? Unless the object will lose the mass or gain extra mass, all right? So these are the basic equation for you to know. And this is a simple example, right? So this rocket will produce this lifting force, T, and this lifting force, T, will overcome gravitational weight or gravitational force, which is called as a weight. Then the net force is equal to T minus W. Then this net force will produce vertical acceleration, AV. Then in the horizontal direction, there's no net force, then acceleration equal to 0. Okay, so this is a very simple calculation. Then how about the angular and the circular acceleration? If let's say object A move along the circular path with a uniform circular velocity, there is still centrifugal acceleration, which is equal to V squared divided by R, all right? Even when V is a constant, all right? So actually the design of a gyroscope could make use of this equation, okay? In order to induce radial acceleration, then radial acceleration could be converted into centrifugal force, right? Then after that, we apply the same principle of design, and we will study this principle of design in the following slide, right? Okay. And because behind every acceleration, there is a force, right? So radial acceleration, and behind it, there's a centripetal force, all right? So, okay. And also we can talk about the centrifugal force, okay? And the centrifugal acceleration. So centrifugal acceleration is move away, okay, from the center of rotation, and the centripetal force is to pull the object, okay, toward the center of the rotation, okay. So these two accelerations are in opposite direction, all right. So let's say this is a mass placed on this rotating platform. Let's say this is a rotating disc, and the A is a mass. Okay. Then when we rotate this, immediately you understand there is a induced centrifugal force. Okay, which will move away. Okay, in the radial direction. All right. So we can make use of this force to induce a value which could be measured by the sensing element. All right, so this is why the design of a gyroscope is more or less similar to the design of acceleration sensor. All right, okay. So then I put this statement here: angular acceleration actually is automatically converted to radial acceleration, which is equivalent to linear acceleration in radial direction. All right, so we can apply this observation to come out a similar design for the measurement of angular motion. All right, okay. And then how to determine the net force, okay, received by a single rigid body inside a complex mechanic system? The answer is what? To use a free body diagram. If you have a mechanic system with n rigid body, then you have an n free body diagram. Each free body diagram only has a single rigid body. For example, we have a mechanic system with a two rigid body, then we must draw two free body diagram. All right, so this is a free body diagram for M1, free body diagram for M2. All right, then in the vertical direction, we must look at the, okay, all the external force acting on the single rigid body. All right, so this is the practice or guideline for us to do analysis of rigid body inside mechanic system. All right, so then here is an example. Let's say we have a vehicle move on the horizontal plane. All right, so we can talk about the free body diagram. Then in the vertical direction, so you will see we have a weight of this vehicle. We have a contact force here, and then because there's no acceleration in the vertical direction, so it means the sum of the forces should be equal to 0. So it means the net force in the y direction should be equal to 0 because there's no acceleration. However, in the horizontal direction, we have a driving force delivered by the engine of the car. We have a L resistive force, okay, coming in from, plus frictional force, okay, in from and in the back. So therefore, the net force in the horizontal direction should be equal to the sum of the driving force, L resistance force, and frictional force. All right, so add them together, then you have a net force. Then this net force should not be equal to 0. All right. And this is very important for you to understand, because the design of the acceleration sensor will make use of this phenomena, which is called as an inertial force. For any linear acceleration, actually we will induce inertial force. All right, then we will make use of this phenomena to guide the design of acceleration sensor. All right, then similarly for angular motion or circular motion, such motion will induce centrifugal force, all right? But the nature of these two forces are more or less the same. So this is why if we leverage on the use of force to guide the design of acceleration sensor, then the design principle will be the same, all right? So for linear acceleration, we use inertial force. For angular motion, we use centrifugal force. That's it, all right? And some design may use Coriolis force, because when there's a rotation plus translation, there is a Coriolis force, all right? So, but usually the Coriolis force is quite small, all right? So centrifugal force should be bigger, okay, than contrary force normally, all right? So let's say we have two objects, they are placed together, right? For whatever reason, all right? So let's say object is placed on object B, A is on B. When B accelerates, in this case, B is a vehicle and A is a person sit inside the car, for example, all right? Okay, when the car accelerates, then A will actually exert, okay, we add a force on the vehicle to prevent the vehicle to accelerate, okay? This force is called inertial force, okay? So person A will exert the inertial force on the vehicle, okay? If both objects will stay together, all right? So mathematically, we can write down this equation, okay? So the reacting force from A, okay, is equal to inertial force from B, okay? Because when the car accelerates, B will produce inertial force. Then the car will produce reacting force. Then these two forces A together equal to 0. So this is why the people can stay inside the vehicle, all right? So then there's no relative motion. Equal to 0 means between A and B, there's no relative motion, all right? Because of this equilibrium condition, okay? So this equation is imbalance, all right? So, and the typical example is like this, all right? So in this situation, when the bus accelerate or when the MRT or the train accelerate, all right? So the person will have inertial force. Inertial force is a negative MA in the opposite direction of acceleration, all right? And you will see the bus or the train will produce reacting force F. You see the person use a hand to hold the handle, okay? Here, then there is a reacting force received by this person. So when this equality holds, then the person will stand still, okay? So this is a typical scenario for you to understand how come when the bus accelerates and our body will go together with the bus, all right? However, in this situation, so you will see the person cannot receive the reacting force. That means the car cannot produce a reacting force acting or on the person. Then in this case, the person will fall, you see, okay? So when there's an acceleration, then since there's no reacting force acting on the person, then this person will fall, okay, off the vehicle. Or when there's an deceleration, same, okay? So deceleration will also produce inertial force. And since the reacting force to the inertial force could not apply to the body of this person, then this person will, okay, fall in front. This is the fall backward, then he will fall forward, right? So this is a typical scenario. I believe every one of you has similar experience in your life, right? Okay, so that's the physics about the acceleration. Okay, so you understand acceleration may exist for linear motion, may exist for angular motion, and acceleration is related to the force, and in particular, acceleration could induce inertial force or centrifugal force, all right? And is this property will be used by us to guide the design of measurement and the sensing system for acceleration, all right? So before we move on to study the direct measurement of acceleration, let's look at the way of doing indirect measurement. Indirect measurement means for whatever reason, we know the value of a related physical quantity. Then in this case, we can directly compute acceleration without doing direct measurement. All right, so we look at this scenario first, right, before we enter the study of how to do direct measurement. All right. So if let's say for linear motion, for whatever reason, we know time function of a position, we know time function of a velocity, then in this case, no need for you to do a measurement of acceleration, because we can directly compute acceleration from position or directly compute acceleration from velocity. I guess every one of you know these two equations. Okay, second order derivatives of a position vector will give you the answer to acceleration. First order derivatives of a velocity vector will give you the answer to acceleration. Done already, all right? So it's very simple. And here is an example. Let's say for whatever reason, let's say we know the recorded time value of a position, then it should be good enough. Then we can determine what is velocity, what is acceleration. Or for whatever reason, we know the recorded time function of a velocity, it should be good enough. Then we can calculate acceleration. And in this case, velocity is linearly increasing. Therefore, acceleration is a constant. So this is a scenario of constant acceleration. Okay, a linear motion with a constant acceleration. So it's quite straightforward. All right. And one more example, if let's say we have recorded data for x coordinate along the x-axis, then what should be the velocity profile or acceleration profile? Then you will see it's quite straightforward. Okay, so here you see we have a motion with a constant acceleration or the velocity linearly increase with respect to time. And during this time interval, velocity is a constant, then acceleration is 0. Okay, during this time interval, velocity linearly decrease, then acceleration is a constant with a negative value, then it means a deceleration. All right, then within this time interval, velocity linearly increase with respect to time, then it means acceleration is a positive constant. All right, so if we know information about the position, or if we know information about the velocity, then it's good enough for us to determine or to calculate the value of acceleration. That's it. All right, so it's a typical example of knowing related physical quantity, then we are able to compute the value of acceleration. All right, and here is one more scenario. Okay, so actually linear acceleration could be computed from a linear displacement of a spring. All right, for example, in a mass spring system, when there's an acceleration, then the acceleration will induce inertial force on the mass. The inertial force on the mass will compress the spring. Okay, until you will reach equilibrium position. Then we can use that information. Okay, assume we have a sensor which could output position information. All right, then it's good enough for us to compute acceleration. All right, so then what should be the equation? So this slide basically shows you the equation. All right, when there's acceleration, acceleration will produce inertial force, and when there's an inertial force compress or stretch the spring, then spring will undergo displacement. So that means this inertial force will compress or stretch the spring. Okay, then the deviation of the spring from its neutral position is theta b. Then this equality holds. Okay, therefore then we know what should be the deviation of the spring from its equilibrium position or neutral position. All right, so equal to ma divided by k. Then what should be the equation for us to calculate acceleration a? So that means both sides divided by m, shift the k towards the left hand side, then you swap the equality, then you have this equation done already. All right, so it's quite straightforward. All right, then here is a slightly more complicated example which make use of knowledge about the spring's displacement in order to calculate acceleration. Then in this case, assume we know the displacement of a mass m1 from its neutral position. Its neutral position is when x1 equal to 0. Okay, when there's acceleration, then x1 will not equal to 0. Okay, then what is the equation for us to calculate acceleration from the knowledge of x1. Okay, so this question. So here we have a mechanic system with a two rigid body. So we have a M1, M2. Then because we only care about the motion in the horizontal direction, then we only draw free body diagram with the forces which will contribute to the motion in horizontal direction. We ignore those forces which will never contribute to the motion in the horizontal direction. All right, so this is a simplification for us to do. All right, so then in this case, in horizontal direction, there's only spring elastic force F2 acting on M1. For example, M1 tend to move, okay, toward the right-hand side. So then the spring K2 will oppose the motion. So this is why you see the direction. When M1 move toward the right-hand side, then the spring K2 will oppose the motion, okay? And the spring K1 will also pull it, oppose the motion as well. So this is why F2, F1 pointing toward the same direction. Then the inertial force, okay, when there's acceleration towards the left-hand side, inertial force will move towards the right-hand side, okay? So this is the inertial force acting on M1. And also M2 will receive inertial force, because they accelerate together, all right? So then spring K3 will produce F3, which will oppose the motion, okay, by M2. But however, you see, M1 will compress spring K2. Then spring K2 will have a pushing force on M2, all right? So then F2 acting on M2 is in the right direction, all right? So this is a free body diagram. Then we can sum them together, okay, then apply Newton's second law. The net force on M1 will produce acceleration by M1. Net force on M2 will produce acceleration by M2, all right? So then what is F1? F1 equal to K, X1. F2 is equal to the total change in length of K2 times K2. So X1 is the change. This is the displacement at the right end of the spring. This is the displacement at the left end of the spring. What is the net displacement? So it's a sum. That means X1 minus X2, right? So this is the net displacement of K2, or change of the length by K2, right? So then F3 basically is under compression, okay? So this is the change of length by K3, okay? So we have these two equations. Now from these two equations, so we just arrange it together. That means put lump all the term in front of X1, in front of X2 together, okay? So therefore we have a coefficient in front of X1, coefficient in front of X2, coefficient in front of X1, coefficient in front of X2, right? So let me call it equation 1, equation 2. Then equation 1 times K2 plus K3. That means this one times K2 plus K3, because we want to cancel out the eliminator. We want to eliminate X2 because the question asks us to relate acceleration to X1. So we will eliminate X2, okay? So we want to eliminate this one. So that means this one will times the coefficient of this X2, and this one will times the coefficient of this X2. That means the second equation will times K2, all right? Then add them together, then this X2 will disappear, all right? Then we only have X1 times coefficient, okay? Then this A together, then we have M1 times this one, M2 times this one. Then both sides divide by the sum of M1 times this one plus M2 times this one. Then we have this expression, all right? And then X1 can take it out, okay? So these are the coefficient, numerator are the coefficient in front of X1, all right? So then this is a formula for us to calculate acceleration if we know, okay, the displacement of M1, okay? Then for angular motion, so it's similarly to linear motion. Okay, if we know for whatever reason angular position, then we should be able to calculate angular acceleration. If for whatever reason we know angular velocity, then we should be able to calculate angular acceleration. All right, and here I just rewrite this statement again. Okay, for rotational motion, so actually in the radial direction, we can consider there is a centrifugal acceleration, and the centrifugal acceleration will produce a centrifugal force, which will act on the mass. Let's say, assume at the point A, we have a mass. Then centrifugal force will push the mass to undergo linear motion in the radial direction. All right, then we can use this phenomenon to come out the design of the sensor, which allow us to measure acceleration or motion of angular rotation. Okay, so then the design principle will be similar. All right, okay. And here is just a simple example. Let's say we have a ball connected to a rod, and the rod is constrained to this joint. So then the ball can undergo motion along the circular path. Let's say at this point of time, we know this angle theta. Okay. Now at this point of time, what should be the radial acceleration? What should be the tangential acceleration? Right. So it's just quite a simple example. So then in this case, we know there's a weight, gravitational force acting on the ball. This force may have a two component. One is in the direction of the rod. Another is perpendicular to the rod. Okay. Then this force component will produce tangential acceleration, and this force component will produce a radial acceleration, such as centrifugal acceleration. Right. So then this force component is equal to mg cosine theta. Mg cosine theta divided by m, so it's equal to radial acceleration. So then we have a g times cosine theta. All right. Then this force divided by m will give us the tangential acceleration, right? So then g times sine theta. So it's quite straightforward, right? And here I'm going to show you a very complicated example. If you are able to understand the detail of this example, I guess you should be very, very comfortable with the computation or indirect measurement of acceleration. All right. If you follow step by step, actually it's not so complicated for you to know the detail, all right? Because the solution is quite straightforward, all right? Okay, here assume we have a car, okay? Or it's like a mobile robot, okay? And on top we have this single degree of robotic arm. You can consider this is a robotic arm, okay? 1 degree of robotic arm, okay? So it's a single link, and here you have a joint, and here we have a velocity sensor, okay? So we should be able to know what is the velocity, all right? So if we know the time function of velocity, actually means what we know the angular acceleration, right? So then this is the payload of this robotic arm, 1 DOF robotic arm, single degree of freedom robotic arm, right? So now we ask you to know what is the relationship between angular acceleration of the ball or of the hand, okay, and the linear acceleration of the mobile base, all right, of the car, all right, okay. So we want to know what is the relationship between x double dot and the theta double dot, all right. So assume this is the x-axis, then vertical axis represents a y-axis, right? So then we have the theta. So then you will see we ignore the mass of the rod, okay? So we only have a ball here and have the mobile base, which move only in the horizontal plane. Then this is the angular position of this rod, okay? So this is the mass of the ball, that's it, right? So then here we can write down some basic equation, all right? So since we have this theta angular position, then first order derivatives, theta dot should be equal to angular velocity of the ball or the roller about the axis which will pass through this joint, right? And this one could also be calculated from circular velocity. This is the circular velocity of the ball, okay, along the circular path. Because when this rotate, then the ball will follow a circular path, okay? So circular velocity divided by the length of the rod, the length equal to L. So actually this is equivalent to the radian of a circular path. So these are the basic equation, right? Then what should be the radial acceleration? So the radial acceleration should be equal to the circular velocity square divided by the radian, right? And now we just substitute V with the value of L times theta dot. Okay, then L square will cancel out the 1. So then we have L theta dot square. Okay, so these are the basic equality. So I write it down here. Okay, so now you know radial acceleration is equal to this. Okay, then what is tangential acceleration? Assume this law will have angular acceleration. If alpha is angular acceleration, then tangential acceleration is equal to L times alpha. Then what is alpha? Alpha equal to theta double dot. So I rewrite this equation here. So then you can remember all these 3 basic equations. All right. So this is the starting point. Now we assume that the mobile base is at the rest. So then it's easier for you to imagine. Okay. So with respect to the mobile base, and then the ball will have acceleration, tangential acceleration, radial acceleration, and because these are the 2 vectors. Okay, so then this vector may have a component in x direction, component in the y direction. Okay, so we just look at the x component of the ball's acceleration. All right, so that means that this is the x component of the ball's acceleration with respect to the mobile base. Okay, P over C. So this is just a notation. Say the acceleration of the ball with respect to the mobile base. So it is not with respect to the ground. Okay, so mobile base. Then, so this is the x component of a tangential acceleration vector. This is the x component of a radial acceleration vector, right? So now we know AT is equal to this one, AR equal to this one. Then we substitute AR with this result, substitute AT with this result. Then we have this equality. So it's very simple, all right? Then in the y direction, so we also have a y component, right? So the y component from tangential acceleration vector, so times sine theta, and the y component from a radial acceleration vector. So remember, acceleration is a vector, so it has a 2 components, all right? So replace AT by this result, replace AR by this result, then we have this equation. So this means the y component of the ball, okay, of the ball's acceleration vector with respect to the mobile base, right? Okay. Now assume the mobile base, okay, has a motion, has acceleration, all right? So then why the mobile base has acceleration? Because there's a driving force, okay? Now you look at the interaction between the ball and the mobile base. Because when this one try to move there, then the ball will try to pull it. So then we see inside this rod, we have a tension force T acting on the mobile base. Then another is in parallel, okay? Tension force T will act on the ball, okay? These 2 are equal and in opposite direction, right? So then in X direction, what is the net force acting on the mobile base? So it should be equal to F minus T times sine theta, sine theta. So F minus T times sine theta, okay? So this is the net force in the X direction, all right? So this net force will produce acceleration, X mobile base double dot by this mass, all right? So then from when we have this force acting on the ball in the X direction, so you will see this one also has a X component force, okay? So it should be equal to T sine theta, so which is opposite to this one. And this external force, net force acting on this one will also produce, okay, the acceleration on this mass MP. So it's the mass of the ball. Okay. So then you have XP double dot. All right. So this is the acceleration with respect to the ground. Okay. So acceleration with respect to the ground is equal to the acceleration of the mobile base plus the acceleration with respect to the mobile base, because this ball is mounted on top of the mobile base. So we have this relationship, right? Then in the y direction, we we do the same for the ball, because in the y direction, the mobile base is 0. There's no acceleration. So therefore, we do not have an equation in y direction. We only keep this equation in the x direction. Then for the ball can move, in the y direction, So then in y direction, so what will be the force acting on the ball? So there are two channels. There's a MPG and also the T times cosine theta. So these two A together, because you point toward the negative side of y-axis. So this is the net force will contribute to the y component of acceleration by the mass MP, right? And since the mobile base does not have acceleration in the y direction, so therefore the acceleration component in y direction is equal to the relative acceleration, between the ball and the mobile base. So these two are equal, all right? So then we have now we can put the equation together, So this is from the equation in the horizontal direction. This is the equation in the vertical direction, Both of them are on the ball, Because this is the equation for the ball in x direction, and this is equation for the ball in the y direction, all right? So now we put them together, all right? And also substitute xp double dot with xc double dot plus x double dot p with respect to the mobile base, Then y double dot, yp double dot is equal to y double dot of a p with respect to the mobile base, all right? So then we have a two equation. Then here we can substitute x double dot p over c with this result, and y double dot p over c with this result. And also we do this calculation. First equation times cosine theta plus the second equation times sine theta. The intention is to eliminate t, because we do not want to know t, So because this one times cosine theta, then this one times sine theta, add them together becomes 0, all right? Then we only have all these terms. Then we do a little bit of simplification, you should be able to get this equation. From here, you will see this is an equation which relate q double dot to xc double dot. Q double dot is what? Angular acceleration. Xc double dot is what? Linear acceleration. Then we have these two scenarios, all right? If we know linear acceleration, xc double dot, we should be able to compute angular acceleration. Or if we know angular acceleration, theta double dot, we should be able to compute linear acceleration, x double dot, all right? Then next question is how to measure acceleration, which may refer to linear acceleration or angular acceleration. As I said before, actually, the way to measure linear acceleration and angular acceleration should be the same, because we all leverage on the use of induced force, such as inertial force or centrifugal force, all right? So measurement principles are exactly the same, all right? So now we want to know how to do direct measurement of acceleration, all right? So here I list down three popular principles for us to follow. Later on, I will tell you that they are more than these three principles, all right? So these three principles should be good enough for us to use, all right? The first one is to make acceleration to induce either inertial force or centrifugal force on the mass, and on this special mass which could produce voltage, right? So this is the first principle. Second principle is to let acceleration cause a mass to undergo displacement. Okay, and this displacement will change capacitance. All right, then by measuring capacitance, then we could measure acceleration. All right, and the principle 3 is to make acceleration to cause a deformation on the special mass, and such deformation will make resistance of a special material to change the value. Then by measuring resistance, then we should be able to measure, okay, acceleration. So these are the 3 popular principles for us to follow in order to guide the design of sensing and the measurement system for acceleration. All right. So if we apply principle 1, then the design solution should be like this, right? So you will see we just add in extra module, okay, to the microcontroller. Here you will see we leverage on this property of a microcontroller, okay? So in which all microcontroller could be considered as a programmable digital sensor of voltage, all right? So it is true because all microcontroller offer these 4 modules. For example, microcontroller has a digital counter. Microcontroller has a voltage synthesizer, okay, which will output analog voltage. And all microcontroller offer this module of analog comparator, okay? So this module will compare the input voltage with internally synthesized voltage. If there's a match, then it will output signal to stop the counting, okay? The counted value, the value inside the counter basically is a prediction of output digital value. If the prediction is correct, then the synthesized voltage will be exactly equal to the input voltage, all right? Then it's a perfect match. Then this module will issue a signal to stop the prediction, right? So these modules are inside microcontroller. Then we just need to add in this module, how to convert acceleration into voltage. If we know this, the solution to this module, then we are ready to implement this type of measurement and the sensing system for acceleration. All right. So next question is how to convert acceleration to voltage. The good news is we have this special type of material called piezoelectric material, such as piezo ceramics. All right. So then here we put the inertial mass. All right. Then when there's a acceleration in this direction, this could be a linear acceleration or radial acceleration, all right? So then this material will output voltage. Then this one could be amplified if needed, okay? We can always scale up, scale down the voltage, okay? Before supply the voltage into the microcontroller, all right? So it depends on the range of this value, all right? So this is not the issue, okay? So this is a solution, okay? So this solution exists in the market, so you just follow this solution. Then you should be able to come out the design of a measurement and the sensing system for voltage. Okay, so this slide basically show you illustration. So when there's an acceleration, okay, this could be linear acceleration or radial acceleration in this direction. All right, then you see the voltage change. So then the output voltage basically give us the value about the measurement of acceleration. So this is a very simple solution done already, all right? Then how to apply principle 2 in order to guide the design of measurement and the sensing system for acceleration. Then for principle 2, then we need to know how to convert acceleration into capacitance, all right? Once we know the capacitance, then we know the solution of converting capacitance into voltage. All right. In one of the previous lecture, we have studied the solution for the design of the measurement and the sensing system for capacitance. All right. Then here we just want to know how to convert acceleration to capacitance. That's it. All right. So then this video show you the solution.
Vehicles and modern consumer electronics are unthinkable without acceleration sensors. The sensors detect a vehicle impact as well as the smallest movements of a smartphone or wearables. The acceleration sensor consists of a signal processing chip and a micromechanical comb-like structure. These combs form a capacitor, and the distance between the microstructures determines its capacity. The blue part of this structure is movable. Depending on acceleration or deceleration, they change their position relative to each other. The resulting change in capacitance is detected by the integrated electronics, converted into a measured value, and output into a voltage signal.
This video shows the function of MEMS accelerometers, which are integrated in our ADMA systems. The MEMS sensor consists of an evaluation unit and a micromechanical comb structure. These combs are creating capacitors whose capacities are defined through the distances in between. The blue marked comb is set in vibration with a specific frequency. As soon as the vehicle is accelerating, the swinging part is pulled to the back of the car. This results in measurable capacity changes, which show the value of the acceleration. When the velocity gets constant, the blue comb is swinging as in the beginning. After the car is starting to decelerate, the structure is pulled to the front of the vehicle. That also results in capacity changes, which can define the value of deceleration. In some ADMA system types, MEMS gyros are also implemented in addition to MEMS accelerometers. The principle follows the same scheme.
All right. So in the video, you see the solution is quite simple. So we use a mass to pick up the inertial force, all right? In the case of linear acceleration, or we use a mass to pick up centrifugal force in case of rotary motion, all right? So the principle should be the same. Okay, so here, for example, we have an acceleration. This acceleration could be linear acceleration or radial acceleration or centrifugal acceleration, all right? So then we have this mass, okay, to pick up the induced force, okay? Then in this case, this mass will move toward the opposite direction of acceleration, okay? Then in this case, the gap between these two parallel plates becomes smaller. Then in this case, capacitance will increase, all right? Then if listen, we also consider capacitance between these two parallel plates, then capacitance between these two parallel plates will be reduced, right? So it's quite straightforward working principle. Then equation involve, for example, when there's an acceleration, then inertial force or centrifugal force, okay, should be equal to negative MA. And this force will be counterbalanced by the spring. So you see we have a spring here, okay, 4 spring to hold the inertial mass, all right? So then we have this equality. Then displacement by the spring should be equal to MA divided by K, all right? Then equation of acceleration should be equal to A equal to K times theta D and M. Then in the lecture when we talk about the measurement of capacitance, so you remember this equation. Capacitance is proportional to area, inverse proportional to the distance between the two parallel plates, okay? At the neutral position, we have a C0 equal to epsilon 0, A divided by D0. And when there's an acceleration, when the movable plate change, then the D will become a D0 plus minus theta D, okay? And the theta D is equal to this one, okay? Now we replace the theta D by this equation. Then we have a capacitance is a function of acceleration here, okay? Since here we are designing sensor, we are not going to do the calculation. So as long as we know the relationship, okay, then when there's an acceleration, capacitance change, then we can get the value, readable value. By doing calibration, then we can relate the output to be equal exactly to the input, all right? So this is just to help us to understand the relationship, okay, or the causality between acceleration and the capacitance, all right? So as long as we have this equation, good enough already, all right? So this is a equation underlying the measurement, all right? Then we can apply this principle to design the measurement of acceleration in one direction. It could be along the x axis, along the y axis, along the z axis, or in the radial direction. All right. Okay. So if we want to measure acceleration in two directions, then we just put the two such a sensor together. That's it. All right. So this is a quite straightforward solution. Then here's another example of doing measurement of acceleration along the x-axis and the y-axis. So you will see a lot of parallel plate, okay, parallel plate, okay. So when there's a acceleration in this direction, so you see the gap between these three parallel plates will change, all right? And also the between these parallel plates, the surface A will change, okay? So because the movable one will in and out. When the in and out means A change, all right? So you see we have a lot of flexibility in the design of measurement and the sensing system for acceleration, all right? Then in this direction, when there's a motion, so you will see the gap between among these parallel plates will change, okay? So we can pick up the value of capacitance quite easily, all right? So that's for the application of a principle 2. Then how's about the application of principle 3 in order to come out the design solution for the measurement and the sensing system for acceleration? Okay, then in this case, acceleration is converted into resistance, then which is then converted to voltage, all right? So then in this case, we just add in this module, which will transform the value of acceleration into value of resistance, because in one of the previous lecture, we have already studied the design of measurement and the sensing system for resistance, all right? So we just need to add in this module, which should be good enough already, all right? Then how to convert acceleration into resistance. So this is one simple design solution, all right? So we have inertial mass or mass. It could pick up acceleration or linear acceleration or centrifugal acceleration, all right? So when there's acceleration, then this cantilever will deform. When cantilever deform, assume here is a strain gauge, then strain gauge will also under compression or extension, okay? So when the strain gauge extend, resistance value will increase. When the strain gauge under compression, resistance value will reduce, all right? So this is a way for us to convert acceleration into value of resistance, all right? So it's quite straightforward, all right? So then it's done already. So like give you the answer to the use of principle 3. And besides these three popular principles, we may have many other principles, all right? And here is one of them. And this working principle is to make use of the property of the light, okay? You see we have this chamber, and the inside we have two mirrors, okay? Then when the light enter, because the mirror will reflect the light, then the light will enter into resonance because we will keep moving, okay, in all direction. Then the gap between these two mirrors will dictate the wavelength or frequency of the light ray, okay, or light wave, all right? So here just show you the input-output relationship. The input light is a normal light without the resonance, okay? And when there's acceleration in the horizontal direction, and this mass will pick up inertial force or a centrifugal force, then change the position of this movable mirror. Then when this gap change, then you will see that will create a resonance, okay? Then the output signal will have a peak value at a specific frequency or specific wavelength, because wavelength is related to frequency, all right? So then you will see input is more or less uniform signal, okay, or light with uniform intensity. Then output, you see the intensity has a peak at the specific value of a wavelength. And the least value of a wavelength is more or less related to the value of acceleration. Okay, so this is just extra reading for you to know. Okay, you can do research in this area and to discover a different design principle for the design of a measurement and the sensing system for acceleration. All right. So as usual, once you know how to transform acceleration into readable value, then you must always remember to do calibration. All right. So previous discussion basically talk about the transformation from acceleration into readable value, yi. By doing calibration, we will be able to produce output value zi, so that the zi is exactly equal to xi. So relationship between xi and the zi will follow this straight line, okay, which is 45 degrees above the horizontal line, right? So calibration is very important, okay? Just remember to do calibration, all right? And also remember to do error analysis, all right? So once your sensor is ready, then you can do repeated experiment, okay? Then based on the observed data, then you can calculate the mean value, standard deviation, etc. Then you can also calculate what should be the systematic error, repeatability error, accuracy. And when you do the experiment, you can make the input to change in the increasing order and make the input to change in the decreasing order. Then you do the comparison to see whether there's a difference or not. If there's no difference, then there's no hysteresis error. Otherwise, there is a hysteresis error, all right? And this information are necessary for you to provide to the buyer of your sensor or user of your sensor, all right? So that's all about the study of today's lecture. So the key takeaway from this lecture is for you to understand the physics behind the physical quantity acceleration. And also we have studied some popular way for us to do indirect measurement of acceleration. And in particular, we have studied 3 principles, which should be able to guide you to come out the direct measurement solution in order to design your measurement and the sensing system for acceleration. All right. Thank you for your attention. I'm looking forward to seeing you in the study of next lecture.